Hello everyone, welcome to the video series where we discuss homework related to chapter section 8.1, equations of lines in 2 space and 3 space. This video series will probably be split into, I'm assuming 3 videos. There's a lot of homework to cover, so let's not waste any more time and jump straight into it. Okay, so here, question 1 asks us write a vector equation for a line given each direction vector m and a point p naught. All right, so this is quite simple. We just plug and chug away into our vector equation formula for a line, that is. So this is how it looks. We have r naught is a point on the line, which is now p naught, and then our direction vector m, and we attach a scalar, we attach a parameter t. Okay, so that answers 1, A, and C. Again, I'm going to be doing some selected exercises from this because I don't want to do everything. That'd be quite a lot to cover then, and this video would probably extend way past what it should. Okay, yep, so we just, the vector equation, we have the known point plus t times our direction vector. Okay, and then the same deal for part C as well. Good. Okay, question 2, write a vector equation of the line through each pair of points. So remember, there's 2 ways. Well, technically, there's one way you write a vector equation of a line. It's with a direction vector and a point. If you have 2 points, though, then you can form a direction vector, and then you can use one of the points as the position vector, which is what I did here. So I did a 2A and C here. So first, I form a direction vector, AB. It's also, in this case, M as well. So I just subtract the coordinates, subtract the coordinates, the x's, and then the y's. So since I'm finding AB, I do B1 minus A1, B2 minus A2. I get 3, 3. And then for my known point on the line, I use 1, 7. Similarly for part C, I first find my direction vector by subtracting the 2 points coordinate-wise, the B coordinates from the A coordinates. Sorry, the A coordinates from the B coordinates. And then get my direction vector AB, which I guess I should also call M in this case. So AB serves the role as M. Okay, and then I find my vector equations here. Okay, not quite too challenging. Problem 5, determine if each point P is on the line. So before I even begin this problem, I want to set up my line, xy, the position vector 3, 1 plus t, negative 2, 5, into its corresponding parametric equations, which I do here. So the x equation is 3 minus 2t, and the y equation is 1 plus 5t. Now I begin the problem. So I'm going to do parts A and C again. And all you have to do is you plug in the components of the point into your parametric equation, so negative 1, 11. And then you check to see if you can get out the same t value for both equations. So you solve for t in both equations. Here I get t equals 2 once I solve, and here I also get t equals 2 when I solve, meaning that this point is on the line because the t values are the same. Similarly, for part C, I already have my parametrics. I plug in my the components of the point, so negative 9 for the x, 21 for the y. I solve for t, but look, here I get 2 different values for t, meaning that this point P is not on the line, as where A was. Okay. Question 6, write the parametric equations for each vector equation. So again, A and C here. This is a transition you should quite easily get used to. So I have my vector equations. To find the x equation, you just do 10 plus t t times 13. That's the x part. And the y part is 6 plus t times 1, which is just 6 plus t. So 10 plus 13t, 6 plus t. Okay? Something you should get quite used to in this unit. Okay, part C, similarly. Now we just have added an extra coordinate, but the game doesn't change. So the x's, it's going to be 3 plus 6t. Y is going to be 0 plus 9t. Sorry, 0 minus 9t, which is just minus 9t. And then the z's, we have minus 1 plus t. It's just 1. Okay? That's the parametric equations. Question 7, write a vector equation for each line given the parametric equations. Also a pretty quick transition. Okay, so you have the parametric equations x equals 3 plus 5t, y equals 9 plus 7t. The points, the numbers at the front, the coefficients at the front of the parametric equation, so the 3 and the 9, that's going to represent your position vector xy coordinates respectively, so 3, 9 here. And then the coefficients in front of the parameter t, the 5 and the 7, that will be the components of your direction vector, so 5, 7. Easy, 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 easy. And if you don't got a coefficient either in front or a coefficient that doesn't include a t or a coefficient in front of the t, then you just automatically assume it's 0. Same game I play here, 1, negative 6, 2, 1, negative 6, 2. And then I have 4. I assume there's a 1 here, and this is a minus 2. So 4, 1, minus 2. Makes sense. Perfect. Boom, boom, boom. All right. Moving on. Question 8 asks us, given each set of, I'm solving A and C here again. Given each set of parametric equations, write the scalar equation. Okay. So for A, I have the parametric equations. And then to find the scalar equations, to find the scalar equation, there's not a jump you can make straight to the scalar equation, but there is a transition you can make from the symmetric equation to the scalar equation. So that's what I'm going to do. So first I'm going to the symmetric. The symmetric is easy. That's, you just isolate for t, which is what I did right here. So I isolated for t here, and I isolated for t here. Okay, and make sure you have no negatives in the denominator. Move them up into the numerator, and then simplify. Okay, so from the parametrics, I'm going to the symmetric by solving for t. Then I equate these two values of t because they're both t, so they should be equal. So x minus 1 divided by 2 is equal to 1 minus y divided by 3. Now we can cross multiply this with this. By cross multiplying, we get this. And then we can just write it in its scalar form like this, like so. I guess a more appropriate scalar form would be with the x in front, but it shouldn't really matter. 3x plus 2y minus 5 equals 0. So that's something you should know. If you want to get from the parametric to the scalar, you got to go through the symmetric. Okay. Similarly for part C, we have the parametric. Get to the symmetric, that's by solving for t. So I have x minus 5 divided by 7. For this first t. In the second one, I have y plus 2 divided by negative 4. Bad notation here. Bad notation in the sense that there's a negative in the denominator. I know I just mentioned that you should never have a negative in the denominator. It should be in the numerator. I was being a bit sloppy here because I know at the end of the day, I don't want the symmetric anyway. I want the scalar at the end. So it made my life easier not to write in another line down. So yeah, same ordeal though. I can still cross multiply after finding the symmetric equation. And from cross multiplication, we get this guy. And I keep writing it in the reverse order. This should be the correct form. Minus 4x plus 20 equals 7y plus 4. Actually, sorry, I lied. So it should be minus 4x minus 7x plus 6 equals 0. But the scalar equation never has a negative in front. That's by convention. So we can factor out a negative. So we have 4x plus 7x minus 6 equals 0. So we factor out a negative 1, divide it by both sides. 0 divided by negative 1 is still 0, so nothing changes. So we have 4x plus 7x minus 6. Again, you can't go straight from parametric to scalar, but you can go from parametric to symmetric to scalar. All right. Question 9, graph each line. This is a quite unique problem. So I did 9A, B, and C for this problem. So for 9A, I can't straight graph from, so this is considered the standard form, this is the scalar form, or standard form of a line as well, as you learned it in grade 9. I can't graph from the scalar or standard form, so I transition this equation into its slope-intercept form, which is, you can get that by solving for y. Okay, and then you have an you have a y-intercept of -6, a slope of -1/2, and that's pretty easy, right? You just do, you're going -1, 2, you're going 1 down, 2 to the right, 1 down, 2 to the right, 1 down, 2 to the right, or similarly, 1 up, 2 to the left, 1 up, 2 to the left, 1 up, 2 to the left. Okay, so that's how you can graph that. I hope you remember that from grade 9, how to graph lines. Okay, the next one, I did B. So B, we're given the vector equation of a line. It's hard for me to interpret how to graph this. So what I did here is I understand that this first component of the direction vector corresponds to a run. The second component corresponds to a rise. So that gives me a slope then of -2.5 or -5/2. And I know at least one point on the line, -1/7. So this is that point right here, -1/7. And then I do that, the same thing. So I'm going -5, I'm going down 5 to the right 2, down 5 to the right 2, down 5 to the right 2, or similarly up 5 to the left 2, up 5 to the left 2. Okay? Question C. So it's hard to graph from parametric equations alone, so I'm going to move to the vector equation of a line first. And then I just do the same thing as part B. So I figure out that this, again, is a run. This is a rise. And I have a known point on the line again. So this slope, the analogous slope here, would be m equals 3/1, or just 3. Okay? And then you can graph again. Actually, there seems to be I think I might have graphed this line wrong. Ignore this one. I think I was doing a different problem here. Yeah, ignore this problem. Just follow the same procedure though. Yeah, sorry, ignore this solution. Sorry about that. Question 10. Okay. Write the scalar equation of each line given the normal vector and point P naught. Okay. So I just wanted to make sure we're recording. So write the scalar equation of each line given the normal vector n and point P naught. So for this one, I did 10a and c. Okay, this one's quite fun as well, actually. So this problem is actually quite easy. You have to recognize that the scalar or standard form of a line, so the scalar standard form of a line is written like ax plus by plus c equals 0. But we know, it's a common fact, that the normal vector to this line is actually represented by the coefficients a, b. Okay, so then I can just plug those in. What I did is I plugged those in for a and b. So 3, 1, right? This is 3, this is 1. I have 3, and I have a 1 here. Okay, and then all I have to do is solve for c. And I can solve for c by just plugging in a node and point, which I have, 2, 4. So then I plug in 2, and I plug in 4 for y. I find c is negative 10, and then the job's finished. 3x plus y minus 10 equals 0. Same thing for part C. I plug in for a and b the components of the normal vector, which is, in this case, 0 for x, 0 for the coefficient in front of x, but 1 for the coefficient in front of y, so I get y plus c equals 0. And then I plug in my point. My point is negative 3, negative 7, so the negative 7 goes here, from here. There's no slot to fill in for my x. I solve for c again, which equals 7, so y plus 7 equals 0. Perfect. Okay. So let's end off here. I'll continue from problem 11 in the next video, and I'll see you shortly.